my name is Murali Rajagopal. I work for VMware. I'm a storage architect there. So today we are going to be talking about NVMe or fabrics and shared storage. And this is a two-part presentation. I will talk about the OS support, and then I'll give you a little bit of a glimpse about how we are supporting in the OS, and it'll give you a feel for the maturity of the support. And that will be followed by a presentation from Madhu. The other speaker couldn't be here. He is going to walk you through some of the controller side of the house in terms of the support for NVMe fabrics. And after that, we will be open to questions. So with that, let me begin. Okay, this is a disclaimer from our company that anything I say can change. Okay, so legal requires it. Sorry. Yeah. Okay, so let's go with this NVMe support in VMware. We support all kinds of storage stacks, right? We have legacy to worry about. We have SCSI to worry about. We have iSCSI, Fibre Channel, everything. And in the OS, obviously, we are not a typical OS like in the guest. So the guest sits above us. And then here we talk to the guest. And then we have our own file system. And below the file system, we have the specifics of handling fabrics. In other words, I'll come to that in a few slides. But I'm giving you the high-level picture here. So today's talk, I'll be focusing not on SCSI, but the NVMe side of the house. With that, this is a high-level picture of the storage stack. On the left side, what you see is a number of layers, and there are gray boxes and green boxes. I'll just give you the overview because I want to keep this at a high level. The gray boxes are essentially the legacy support in terms of SCSI. And we are now trying to give a NVMe support end-to-end. So it's not completely green. And the green boxes kind of indicate what the NVMe support is at different layers. I'm going to zoom into some of these layers in the next few slides, so wait upon this. So if I look at the drivers, which is at the very bottom, and I'm on the right side of the picture is an expansion of the driver architecture. The way it works here is it's very modular. In the middle layer, you see a transport framework under which you can plug in a number of drivers. PCIe being local device being one of the drivers. We will be supporting Rocky RDMA and Fibre Channel to start with. And that's coming in the next release of ESX, which is right around the corner, but I can't talk about it because I'm not a product manager. But anyway, so that's right around the corner. And above that, you have two boxes here. One talking to the SCSI side of the house, the other one is NVMe. And here, the idea of this chart is to basically show that we are involved. As we release different vSpheres releases, we will be continuing the support in terms of NVMe features. I'm not going to go through all of them, but to call out that the current release is 6.7, which is inbox, and that supports namespace management and things like people who are familiar with NVMe, they will understand what I mean by async event error handling. That's an important feature in NVMe. In future, which is right around the corner, but I can't talk about the date, like I said, we'll be supporting the NVMeoF fabrics. Like I said, we'll be talking about, we'll be supporting RDMA and Fibre Channel. And in future, we'll most likely support TCP. We have a whole list of NVMe features that we'll be supporting, including reservations that's coming in future. The idea is not to spend too much time here on the driver itself, but I want to spend a little time on the core storage. This is a place in our stack where we actually support the multipathing. And what we did in the previous architectures is we allowed vendors to have plugins that are very specific to their arrays, for example. This is for the shared VMDK storage. In the case of NVMe, we support something called a high-performance plugin. And basically what it has is it's optimized for NVMe. It has wider lanes, it's almost lockless, and it has other optimizations that I won't go into, but enough to give you the idea that the NVMe stack is being developed actively. This is a place where you have multipathing support. In terms of the features, very soon you will see announcements on NVMe multipathing. There's a spec called ANA, which is critical to the multipathing in NVMe or Fabric space, and we'll be supporting that as well. In future, we'll do the complete end-to-end NVMe, which is not there. We still have some SCSI level, SCSI level operations inside the stack at this point in time, even in the upcoming release. We also have a virtual NVMe device that sits directly below the guest. And its job is to interface with the guest operating system. And this is an emulated version of the software. It's not a para-virtualized version. This particular stack, we've been supporting it from the very first NVMe spec. And the whole idea of this chart is to tell you that we will be supporting this with the upcoming NVMe specs, and we'll be supporting the 1.3 spec pretty soon here, along with all its rich set of features. So that was a very quick, fast breeze through the OS because I didn't want to spend too much time there. I want to go to the next topic, invite my co-presenter here.
Hello everyone. My name is Madhu. I work at NetApp. I'm an MTS at NetApp. And today I'll talk about the NetApp ONTAP NVMe or Fabric architecture. So Murali already touched upon from an ESX host perspective, and I'm going to go on to the array side of things and talk about it. So before I begin, small plug here, right? I mean, we are a series of firsts in the industry from NetApp perspective in the NVMe over Fabrics technology area. Here's what we have already done, right? We came out with the first NVMe over Fibre Channel solution back in 2018 with bare metal SUSE Linux. In December, which is our cadenced release for every 6 months, we came out with ANA, the ANA support. We brought in Red Hat Enterprise Linux. May 19, we have Windows support, and then came ESX support, which obviously when ESX completes its qualification, we'll be ready for it. And again, here's a key point here. This is supported on all our all-fast flash arrays, AFF arrays, which contain 32 gig fiber channel ports right now. So there is no upgrade needed in terms of hardware or fabric. So again, like I said, no hardware fabric needed, no licensing costs. It's a seamless migration with zero copy from SCSI. So customers who have SCSI LUNs today, with a software upgrade, will be able to move to a much faster protocol that does NVMe or Fabric. And there's a technical article over there on the web for people who are more interested in seeing how this flows. In the next few slides, I'll go over the NetApp architecture, some of the protocol objects that we have, how it maps into NetApp, the performance that we are seeing, and the future direction of where we are going. So some of the things that we tried to look at was the core design principles when we were building this architecture. So when Flash came along, there was a huge shift in how we think, right? I mean, from our spinning Rust to Flash. As part of that, we had to do a bunch of performance improvements within the ONTAP stack. While we were doing the performance improvements, we came into some core design principles that we have here, which is like trying to have lockless implementations, zero context switching, a polling mode. I mean, interrupts are a decade back now, so it's all polling mode, small code path length, dynamic threading, and zero copy. So these were our core design principles that we used when we were trying to improve our SCSI stack. And these are the same core design principles that we have been using to build a ground-up NVMe over Fabric stack in ONTAP. Again, all of this seems common sense, but when you start implementing it, there's a lot of issues, especially when you try to do this in a parallel mode. So the other thing when we are talking about, any questions? Okay. So the other thing when we are talking about developing a new product is to have innovation velocity. It's one thing to say, oh, you got all these design principles, but we also need to get a product out into the market. So there were a couple of things we did. The first thing was to reuse whenever possible. So we leveraged the existing SAN management stack within ONTAP, within NetApp. We leveraged the existing FCP driver in terms of the configuration and the management of the target ports. Then we built flows in wherever we could. But then we knew that our data plane, the architecture to actually pass I/O, needed to improve. So we built a ground-up data plane architecture here. We also partnered wherever possible. So since our first solution was with Fibre Channel, we partnered with Broadcom for the FC transport layer. In fact, the partnership produced code that today has been open sourced. That the part of the code which Broadcom and NetApp developed together is in the SPDK branch right now. So all in all, with reusing wherever possible, partnering wherever possible, and using our core design principles, it took us about 9 months to develop a new blocks protocol, and this was back when we did our first release. So I'm not going to spend too much time on this, but this was the open source leverage that we used with SPDK. I think a lot of people here are familiar with SPDK. This is a little bit of a dated slide, but this represents how we looked at SPDK from our side. And there were things in there that got us excited because they have a lot of the same principles that we needed to use and we were using in our SCSI stack. For example, a poll mode driver, no interrupts, a lean and optimized code path. There are a few things that we had to improve upon. For example, SPDK, at least when we started, was very heavily dependent on DPDK being there. And we actually worked on building an environment abstraction library in SPDK that's been open sourced right now. Then the other thing was there were a static number of threads, and that doesn't work well for us. We needed a dynamic threading policy that could allow us to ramp up threads and ramp them down as needed, depending on the load on the system. But at a high level, this was the open source, so Intel-powered SPDK, and we used this and we built our solution using this. So from a top-level architecture, right, so we had a SCSI protocol, right? So we had our SCSI target component, which was at a 10,000 feet level. There's a SCSI protocol stack, and then there's a Fibre Channel, driver below it. And this interacts with the other NetApp parts, which is our file system, which is Waffle, and then our management system, and of FC physical port. So when we built NVMe or fabrics, again, like I mentioned this before, we reused some of the existing places. So it's the same backend. It's the same, whether it's a LUN or a namespace. It could be anything on the backend as when you're talking about NVMe or fabrics, right? So we used Waffle. We used the exact same management control plane and a same physical port. So what I mean is you could have that same target port, the FC port, that could run SCSI and NVMe over fabric at the same time. And deliver both protocols, on the same fabric. So when I look at that NVMeoF target component, right, I could blow it up a little bit more from the previous picture. If you, when I go back here, this NVMeoF target component, if I were to blow that up a little bit more, we can see how it maps to all the the SPDK components in here. So we have there's an event reactor framework which comes from SPDK. We use the same thing. We built the environment abstraction layer, which allows us to take the SPDK, the core NVMeoF library and adapt it to a kernel ONTAP ecosystem. And the FC transport is there, which we built with Broadcom, and now that's gone back into the open source land. The BDEV and the Waffle interfaces, for folks familiar with SPDK, those are the block device abstraction layers. Any questions so far? All right. So the next slide is going to talk about the protocol objects that we have. and how it maps into the ONTAP protocol objects, into the ONTAP management. Again, for folks familiar with NetApp and ONTAP, the management does not change. It's the same management model that we have. So at a high level, right, NVMe or fabrics, there's a bunch of hosts. They go through a fabric, and there are fabric ports involved. So, and then there is a subsystem. This is the NVMe subsystem that's within connecting into a fabric. And then you have namespaces. So when a host connects into a fabric, into a subsystem, which is the target, via the fabric, it establishes a controller. A controller is a protocol concept here which provides a set of queues. It's a protocol endpoint for, if you can think of it like, visualize it like that, which is very different from SCSI, which had a LUN as an endpoint, or a ITLN, I guess, as an endpoint. And the controller has a bunch of queues. So the NVMe or fabric specification, what it does is it mirrors the core NVMe specification in that the controller has an admin queue for doing administrative commands and a bunch of IO queues, which run parallelly for all the IOs that you need to run. So looking at this protocol object, okay, yeah, there's a submission queue and a completion queue. So it's the same that you would have, whether it's an FC transport or an RDMA transport, or tomorrow if there's a TCP transport. Looking at that object model, and if I were to map it into an ONTAP object model, our core multi-tenancy solution is called as a VServer. It's a storage virtual machine. And within that VServer, we build subsystems, which is the same as the NVMe subsystems that we have. And then we create namespaces. Namespaces are in the VServer container, if you can say so. It's not a container, but logically speaking. And then you map these namespaces into a subsystem. So a subsystem owns namespaces. The namespaces do not reside outside of a subsystem. And then you have lifts. Lifts are logical interfaces which are within a vServer. It exposes an interface to the fabric for that tenant. The hosts that we come into picture are part of our access control list. So you need to know which hosts to let through. You need to know what QoS to give to the hosts, etc. And that's the ACL that we use here. And then a host comes in via the fabric and creates a controller, and then talks to namespaces that it's allowed to talk to. And the controller, again, has the set of queues that both the host and the target sees. Both of them know exactly what is the queue depth, what are the number of queues, so that they can actually talk to each other, and flow control is almost implicitly available because of that. A new host comes along, a new controller is done. So from a performance perspective, I mean, this is a very generic slide, and I have a specific slide next to it. But what it's showing is, compared to FC, the latency, how it drops in NVMe or Fabric, and as we go along, the x-axis is the IOPS. And again, what I want to emphasize here is, at least from a NetApp perspective, what we found was that the majority of the latency that we were seeing today was in the fabric, well, meaning the solution, the protocol solution. And when we go back here and see, when we did these things, these design improvements, which is the pole mode driver, we optimized the code, we brought in a lockless design, we minimized context switches, we brought in a dynamic threading pool. When we did that, even if I had the same SSD at the back end, and we have the same SSD at the back end, we still saw a huge drop in latency and higher throughput with lesser CPU. And the reason is the protocol itself lends itself to parallelism. It gives us that capability to make it parallel. And so eventually we ended up with about 1 million IOPS. This is an A800 with 10 nodes of bare metal SUSE Linux with 75% read and 25% write. We got about 1 million IOPS at around 0.5 milliseconds, and at 100 microseconds latency, we got up to 700K IOPS on a single array. And again, we had the same backend. The backend did not change here. It was the improvements in software and the parallelism that brought in these changes. And the protocol itself, of course, the NVMe or Fabric protocol. The different lines here represent the different ONTAP releases. And again, you can see that our FCP or our SCSI lines have also changed because it's again the same design principles of not having interrupts, of reducing locks, of not doing context switches, of polling, etc. These are the things that result in the improvement. So the next steps, what do we have coming up, right? And again, this is a disclaimer that we have that things change. Dates are not included because I don't speak to them, and plans and priorities of any company keeps changing. But from what we are looking at immediately in the future, the first thing is to do protocol currency, which means we need to keep up to date with the standards. So there are relevant TPs that are coming out, and we will support all and any TPs that we need to support for our partners and for our business. An example would be like, there's a few TPs here that I mentioned. I actually don't know the details of each of the TPs offhand, but these are the TPs, for example, that allow us to increase the number of namespaces, to do specific identify commands within the protocol that allows some of our partners to work more seamlessly. And then, of course, reliability and availability. Those are the other two things that we always want to do. Other than protocol currency, we have some big ticket items that we are still working on to get to completion in this space. The first one is the NVMe reservations. We need to, the protocol has reservations available. We need to get that running. And the next two are a couple of transports that we need to do. So we came out with FCP. We need RDMA transport to come out next, and that's what we will be working on. And the other thing is TCP transport, which is going to make this protocol even more ubiquitous.
So we'll continue supporting all these features. So you saw the complementary side on the host that allows companies like NetApp to support their offerings. So we'll continue to do that, including reservations, like you mentioned. There's a whole laundry list of them, including all the technical proposals that are being spun out of NVMeoF.org. Also, we are involved in the SNEAS management effort to standardize the JBoF management that's going on in the Swordfish group, and I'm part of that group myself. So these are the future directions, and I can't announce dates, but in the next offering of the vSphere, which is right around the corner, you can expect both the Fibre Channel and the Rocky support, and in future releases, maybe TCP. Okay.
Thanks, Murali. So if there's a key takeaway here, one of the things I would say is NVMe or Fibre Channel is a mature product that's available out there. It's got a mature ecosystem right now. It's got compatibility with Windows, with Linux, with ESX, and you really don't need any hardware upgrades, especially if you're on Fibre Channel, to be able to use it and use all the benefits that come with parallelism and a simpler protocol to manage namespaces. All right, guys, thank you very much.